Hello, and welcome to our video covering section 8.1 of your textbook. In this video, we will discuss symmetric matrices and then dive right into proving the spectral theorem. All right, I'd like to start with a quote from Gilbert String, a professor at MIT. In his book on linear algebra, he says, quote, "It is no exaggeration to say that symmetric matrices are the most important matrices the world will ever see." And he says this is true both in the theory of linear algebra and also in the applications. And this is a bold statement, which should be probably pretty surprising to you given where we are in the semester. But let's just recall some examples of symmetric matrices we've seen so far. So one, we've seen orthogonal projections, and maybe you never really noticed this, but orthogonal projections have always been symmetric matrices. Same with reflection. Once again, always a symmetric matrix. Outside of this class, the discrete Fourier transform is a symmetric matrix, and this guy's got to be up there in some of the top symmetric matrices of all time. This has applications in signal processing and data compression, hugely important in our modern world. And then abstracting further, the differential operator, the negative Laplacian, is a quote-unquote symmetric linear transformation if you choose your function spaces correctly that you are trying to apply this differential operator to. And this has applications in my own field of fluid dynamics. And I'm just going to say apparently because I don't really know anything about this, but I've seen it said that symmetric differential operators play a foundational role in quantum mechanics, which is pretty cool. And if you're like, wait, what does it mean to be like a symmetric operator between function spaces? Ask me in class. That's not a topic for this video. But all right, what do we know so far about symmetric matrices? Well, just looking at your book, we've got the definition. It says that a square matrix is symmetric if it's equal to its transpose. And then doing some control F, we would see that, we also have this theorem in section 5.3 that says the matrix of an orthogonal projection. Well, if you are projecting onto some subspace V and you get an orthonormal basis of V, you Gram-Schmidt that bad boy, then it says the matrix of orthogonal projection can be given by some matrix Q times Q transpose, where Q is the orthonormal basis of the space that you're projecting onto. And then you get down to the end and it says, note, this matrix P is symmetric. And then they go ahead and prove that it's symmetric by taking the transpose, using the properties of transpose, where you take the transpose and you distribute it across multiplication, and that means you have to flip the order, and then the transpose that's transpose is the original matrix, and there you go. And I'm pretty sure that's it. And from this alone, you would never guess just how important symmetric matrices are. And really, what it all comes down to is the spectral theorem. This is what gives symmetric matrices their power. So what to look forward to in the rest of this video? You've seen the benefits of orthonormal bases for calculating projections. And you've seen the wonders of diagonalization. You won't believe your eyes when you see what this section has in store for you. Orthonormal eigenbases. Oh yeah. Tell your friends. I can't sell this anymore. This is too dumb of a gag. But anyway, orthonormal eigenbases are going to be the focus of much of the rest of this video. So we've got a motivating question here. For which matrices does there exist an orthonormal eigenbasis? So not just an eigenbasis so you can diagonalize, but an orthonormal eigenbasis. Well, first, let's just note that if you have an eigenbasis for an n-band matrix A, then recall this means that A is diagonalizable. where, okay, we've got S inverse AS is this diagonal matrix B, where you've got the eigenvalues. These could have repeated eigenvalues, but this is up to multiplicity, lambda 1 through lambda n. And the matrix that diagonalizes A is this matrix S, where the eigenbasis are these basis vectors are the column vectors of the matrix. So, okay, this is just theory that we've seen in chapter 7. And now, if our eigenbasis is in fact orthonormal, then the columns of S are orthonormal. And if you recall, that means that S is an orthogonal matrix. So let's recall some facts about orthogonal matrices, because those are going to become important. Okay, handy dandy summary tables. One of the things I like about your book is that it does this. So if you have an orthogonal matrix, this kind of by definition means that the transformation preserves length. And then we've seen that this means that the columns form an orthonormal basis, and then we've proved that the A transpose A is going to be the identity, which really means that the transpose is the inverse. And then we've also seen that an orthogonal transformation or orthogonal matrix preserves the dot product. But really, this right here is going to become important. So for an orthogonal matrix, its inverse is its transpose. And this actually tells us, or we can use this to prove that if a matrix has an orthonormal eigenbasis, then it has to be symmetric. So let's do it. Let A be quote-unquote orthogonally diagonalizable to some diagonal matrix D. So orthogonally diagonalizable means it's diagonalizable and its eigenvectors, or the eigenbasis, they're orthonormal. So this is what I mean by orthogonally diagonalizable. So, okay, it's diagonalizable, so matrix D. So we've got A is S, D, S inverse. And since the eigenbasis is orthonormal, our matrix S is orthogonal, so S inverse is the transpose. Okay, now let's compute A transpose. Well, let's use the property where if you take the transpose of a product, then you kind of distribute it and you flip the order of everything. And then use the fact that the transpose of the transpose is the matrix itself. Whoa, I think it kind of popped up there for no reason. Anyhow, but as you can see, we once again get back our expression for A. So in fact, if A is orthogonally diagonalizable, it's equal to its own transpose. It is symmetric. Yeah, like that. But dudes, the crazy part is that the converse is also true. So it's not just if it's orthogonally diagonalizable, it has to be symmetric. But if it's symmetric, it has to be orthogonally diagonalizable. And for those of you who are wondering, yeah, dudes is 100% a gender neutral term in my vocabulary. I'm from California, where all things are dude. I even called my mom dude. So, yeah, it's fine. All right, so now we come to the spectral theorem, where the number of exclamation points is directly proportional to how awesome this theorem is. Okay, so the spectral theorem says a matrix A is orthogonally diagonalizable. That is, there exists an orthogonal matrix S that diagonalizes A, if and only if A is symmetric. Okay. I was going to say let's prove it, but actually I'm remembering now. Let's look at an example before we dive in and prove it. So suppose we have some symmetric matrix, this one, 4, 2, 2, 7. Then we should, if the spectral theorem is true, be able to find an orthogonal S that diagonalizes A. So how do we do this? Well, as part of your pre-assignment, you've already shown that the eigenvalues of A are 3 and 8, and that it's got corresponding eigenvectors 2, -1, and 1, and 1, 2, respectively. And you've shown that these two are, in fact, orthogonal to each other. So our matrix A has these two eigenspaces, and these eigenspaces are orthogonal. And now to find the orthogonal matrix S that diagonalizes A, we just have to make these eigenvectors unit vectors. And so, all right, divide by their lengths. And then there you go. S here, this is a orthogonal matrix, and theory tells us that S inverse AS is going to be equal to the diagonal matrix that has the eigenvalues on the diagonal. So there we go. We've got our orthonormal eigenbasis, and we have orthogonally diagonalized A. But okay, so spectral theorem told us we should be able to do that, and we were able to do it. But now let's prove the spectral theorem. And I guess really what I'm doing is proving the converse, because the first direction we saw, that was just a couple lines, and that was pretty easy. This direction is going to be several slides. Okay, the first key to proving the spectral theorem. First, we're going to need to show that if we have a symmetric matrix A, and we have two eigenvectors with distinct eigenvalues, then those eigenvectors have to be orthogonal. So this is basically saying the eigenspaces of a symmetric matrix are orthogonal. So this is really key. So let's see why this is true. So let's get our hypotheses on the table. Suppose we've got two eigenvectors with distinct eigenvalues, lambda 1 and lambda 2. Our goal is to show that v1 and v2 are orthogonal. So let's compute this product, which you're like, why? And the answer is because it works. So let's see where this goes, and then you'll see why we're computing this. So we're going to compute this product in two different ways. So first, okay, v1 transpose times a v2. Well, since v2 is an eigenvector with eigenvalue lambda 2, we take that. A v2 is just lambda 2 v2. And then pulling out the lambda 2, recall that that a column vector transpose times a vector is equal to is the same as dot producting it. Excuse me. Okay, so we have that. And now let's compute this a slightly different way, where now we are going to group v1 transpose with A, and then say, okay, well, A, since A is symmetric, A is equal to A transpose. And then using the property that the transpose of a product is equal to the, you distribute and flip the order. So in fact, if we're grouping v1 transpose and A transpose, this is equal to A v1, that whole quantity transposed, times v2. And then recall, now v1, it is itself a eigenvector, and so a v1 is lambda 1 v1. And so we're taking this whole thing transpose, pull out the lambda 1, and then recall that v1 transpose v2, that's just the same as the dot product, it's v1 times v2. So in fact, we've computed the same thing two different ways. We get these two solutions, and now I'll just compare the results. This tells us lambda 1 v1 dot v2 has to be equal to lambda 2 v1 dot v2. And so, okay, just rewrite this. This has to be 0. But remember, lambda 1 is by hypothesis distinct from lambda 2. So this is not 0, which means v1 dot v2 has to be 0. And that just means v1 and v2 are orthogonal. All right. So if we're trying to prove that every symmetric matrix has an orthonormal eigenbasis, showing that the eigenspaces are orthogonal is all right, our first step, and I consider that done. All right, second step. We have theorem 8.1.3, which says a symmetric n by n matrix A has n real eigenvalues if they're counted with their algebraic multiplicities. So, okay, now we're saying, all right, eigenbases, or yeah, the different eigenspaces are orthogonal. And now we're saying that the matrix counting the algebraic multiplicities has n real eigenvalues. So prove this. And just remember, thanks to the fundamental theorem of algebra, we know that A has n complex eigenvalues counting multiplicity, but we want to show that these are, in fact, real. So, okay. Suppose we have two complex conjugate eigenvalues. So we've got P plus or minus IQ. These are eigenvalues of A, and they have corresponding eigenvectors, V plus or minus IW. So we saw this in the complex eigenvalue section. And now we want to show that these eigenvalues have to be real. That is, that Q has to be 0. So first, we're once again doing a unmotivated calculation, or I guess the motivation is it works. So I believe you did this in your pre-assignment. So calculating V plus IW transpose times V minus IW gets you the length of V squared plus the length of W squared. And now we will compute this product, V plus IW transpose times A times V minus IW. We're going to calculate this in two ways. So first, we are going to use the fact that V minus IW is an eigenvalue of A, eigenvector. So it's an eigenvector with eigenvalue P minus IQ. And then, all right, factor out the P minus IQ and use this calculation that we did above. And so V plus IW transpose times A V minus IW has got to be equal to P minus IQ V length of V squared plus length of W squared. Okay. Now we're going to use tricks like we used before, where now, okay, V plus IW transpose. Well, we're going to use the fact that A is symmetric, and then so A is equal to A transpose, and then we will, and then just note that, okay, that means that V plus IW, all of this quantity transpose is in fact equal to what we have here, times V minus IW. Okay, now use the fact that V plus IW is an eigenvector. Oh, I got it right that time. I said eigenvector, not eigenvalue. Okay, and its corresponding eigenvalue is P plus IQ. And then once again, we have V plus IW transpose times V minus IW transpose is just length of V squared plus length of W squared. And then just like before, compare coefficients. We see that P plus IQ has to be equal to P minus IQ, and that's only true if Q is 0. So there we go. A symmetric matrix has only real eigenvalues, and calculated with their multiplicities, they all add up to the dimension of your space. So, all right, we're almost there. We've got that symmetric matrices, their eigenspaces are orthogonal to each other. They have n real eigenvalues. Now, what we need to show is that every single eigenvalue has, I guess, we want the geometric multiplicity to equal the algebraic multiplicity. Because if that happens, then we have eigenvectors that add up to the dimension of the space. We have we'll have n linearly independent eigenvectors, and then we can just diagonalize we can use Gram-Schmidt to find orthonormal bases for the eigenspaces, and then the eigenspaces are orthogonal to each other, and we are good. So really, the last key to proving the spectral theorem is this. And sadly, this theorem isn't explicitly stated in your book. It's kind of buried in the proof that your book gives, which relies on induction. And I'm gonna, avoid using an induction here. So the third key is that if you have a symmetric matrix, then the geometric multiplicity of an eigenvalue is equal to its algebraic multiplicity. And once we have that, we are done. We've proved the converse of the spectral theorem. So, okay, let's prove it. So suppose we have the geometric multiplicity of some eigenvalue lambda 0. Suppose that equals m. So what we're saying is, so remember, geometric multiplicity is the number of linearly independent eigenvectors you have corresponding to that eigenvalue. So let's say there are m. Then, all right, let's let v1 to vm be an orthonormal eigenbasis for the eigenspace. Again, find your m linearly independent vectors in Gram-Schmidt until you get v1 to vm. I mean, in theory, don't do it in practice. It's such a pain. Make a computer do it for you. But okay, so you've got your orthonormal basis for your eigenspace, e lambda 0, and then let vm plus 1 to vn be an orthonormal basis for the orthogonal complement of e lambda 0. And right now we're not claiming anything about its relationship, the orthogonal complement of e lambda 0 and its relationship to the other eigenvalues. Right now we're just saying you've got your eigenspace e lambda 0, take its orthogonal complement, find an orthonormal find an orthonormal basis for the orthogonal complement. And now make S a matrix out of these two bases. v1 to vm, the basis of the eigenspace, and then vm plus 1 to vn, the basis of the orthogonal complement. Then this basis, our matrix is represented by this basis B, where, okay, remember v1 to vm are all eigenvectors with eigenvalue lambda 0, and so there are going to be m columns here. And then vm plus 1 to vn, all right, who knows what these are going to look like in the matrix B, but are given this S and B, A is similar to this B, and B is S inverse AS. And then one thing to notice is that this S is an orthogonal matrix because we took our eigenspace, found an orthonormal basis for it, and then took the orthogonal complement. So just by definition, the space that's orthogonal, and we found an orthonormal basis for that. So yes, indeed, this matrix S is orthogonal. We're going to use that to show that actually this matrix B has to be symmetric. So let's see. Let's take the transpose of this matrix B. Well, B transpose is S inverse AS transpose, which is, okay, distribute and flip the order. We've seen this a bunch of times now. And then recall that since S is orthogonal, S transpose is equal to S inverse. And again, S inverse is equal to S transpose, and then the transpose of the transpose is just the original matrix. So there you go. We get B is equal to S inverse AS, and B transpose is equal to S inverse AS. So B is symmetric. Which means, okay, if we're going to make this matrix symmetric, all of these zeros down here have to have corresponding zeros when we flip across the main diagonal. And then I'm just going to write C as like the n minus m by n minus m matrix that you get here at the bottom. And this matrix C is also going to be symmetric, but I don't think we end up using that fact. But okay, so we have this representation of the matrix B. And recall, since A and B are similar, they have to have the same characteristic polynomials. This is theorem, I don't actually remember, but we totally talked about this. It's true. Okay, So what this means is the characteristic polynomial of the matrix A is we could calculate that by finding the determinant of, instead of A here, putting B here and having B minus lambda in, because A and B are similar. And so, all right, let's calculate determinant of B minus lambda in. That means we've got lambda 0 minus lambda, all these minus lambdas down, and then minus lambdas down the diagonal of matrix C. And if you're going to calculate the determinant now of this matrix, well, if you do Laplace expansion, you'll have to do lambda 0 minus lambda times this determinant, and then plus and then 0 times all these other, like, whatever, minors, I think is what they're called. And so if you do the Laplace expansion, you'll end up with taking lambda 0 minus lambda m times for all of these columns. And then that is going to be, you'll have to multiply that times the determinant of C minus lambda I. Okay? And now the key is to see the matrix C can't have lambda 0 as an eigenvalue. And the reason is, well, if it did have lambda 0 as an eigenvalue, then it would have to have a corresponding eigenvector W. But then you could get another linearly independent eigenvector with eigenvalue lambda 0 for A, or for B, because then you would have 0 down to W would be, this would be another lambda 0 eigenvector for B. Sorry, so it would be an eigenvector for B, which means there would be a corresponding linearly independent eigenvector for A, but that contradicts the fact that we only have m linearly independent eigenvectors. So matrix C can't have lambda 0 as an eigenvalue, which means determinant of C minus lambda in minus m, this cannot have a factor of lambda 0 minus lambda. And so this means that, in fact, the algebraic multiplicity of lambda 0 and the characteristic polynomial of A, it's got to be m. All right, so we've done it. This was a hard-fought battle. There's a lot of slides in this one. I mean, tons of stuff packed into here. But it is worth it. It is important enough that, you should know why it's true. So, okay, some final thoughts. 1. So in the first slide, I claimed that orthogonal projection is always a symmetric matrix, and also that reflection is always a symmetric matrix. And these are actually consequences of the spectral theorem. And it's a good exercise to reread the spectral theorem and think about these transformations and convince yourself that that they really are consequences of the spectral theorem. In fact, it's such a good exercise, I think I'm requiring it for your pre-assignment. Okay, that's enough for one video. See you in the next one.